Okay, I recently just added this page because previously we saw this side view of what happens when that magnet approaches that solenoid and how that current is induced in that wire. So I decided to also include that top-down view for this scenario. So our first scenario is saying, okay, what happens when our magnetic field is pointing out of the page? So I can represent like this. So we have a magnetic field pointing out of the page. So this loop is inside a field. Out of the page we use dots, into the page we use X's. And it's saying what happens when the magnetic field increases. So right now I just represented like it's some field, and we can see there's 4 magnetic field lines passing through. Again, it's not discrete lines that are passing through this loop. It's just it permeates through all that space, but we just use that further apart dots to represent a weaker field. Closer, like more dense dots would represent a stronger field. So as the magnetic field is increasing, like for example, I can draw like this. Just quickly draw some dots around. So it went from like 4 dots going through to 9. So our field's increasing. So Lenz's law states that it wants to oppose a change in flux. So the magnetic field is getting bigger and bigger and bigger out of the page. So this loop doesn't like change, kind of wants to stay the way it is. It likes normalcy. It's going to create its own field. It's going to oppose this change. So it's getting bigger out of the page. So it's going to create a field that goes into the page. Take our right hand, our thumb points into the page because that's the direction of our magnetic field. We can see our right hand fingers are curling clockwise around this loop. Next one we have is it's decreasing. So originally I said we had those 4 dots again. It's inside this field. And later on this field got weaker. So it went from 4 to 1. Okay, here's our loop. It's getting smaller and smaller and smaller. Again, this loop doesn't like change, so it's going to create its own field. This field is going to add to it. So take our thumb, points out the page, our current goes counterclockwise. Other 2 scenarios. So as a field points into the page, okay, X, 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 X. Just draw those X's to represent that field going into the page. I'll preemptively do it for this one as well. Okay, draw those X's. And it's increasing for this one. So it's going, I'll just use the same density of lines I did for the previous example. Previous 2 examples. Okay, so it's getting bigger and bigger and bigger, that field. Again, it wants to oppose that change. So the opposite of getting bigger into the page is out of the page. Okay, it's getting bigger and bigger and bigger out of the page. We're going to have a counterclockwise current. For this one, X, it's getting smaller. It doesn't like change. It's going to create its own field also into the page. We end up with this clockwise current. Key thing to remember for these things is that a current is only induced when there is a change in magnetic field. So if we had a loop going through a unit, so let's say this is like a uniform electric field. And when we draw like this, it doesn't mean like there's no electric field in this space, or no magnetic field in this space, or no magnetic field in this space. We're saying this whole area has the same measurement of magnetic field. It permeates through all the space. These X's are just a representation saying that. It kind of just represents like how strong that field. Again, if you draw more X's in there, it means there's a greater magnetic field. If you draw fewer, it's less. So let's say if I have a loop traveling through here, as it enters, a current is going to be produced. So a non-zero current rolls out because it went from no field to yes field. So during this transition, as that thing passes from this point to this point, it will create a current. As it's moving through here, as it's moving in the middle, there will be no current produced, because as long as it's within this field, the magnetic field strength is the same. And then as it leaves from here to here, yes, we'll get a current again, non-zero current. Okay, so hope that helps with Lenz's law if the previous ones you found though confusing.